Hello again. Please join me in welcoming our next speaker, Dr. Rodrigo Hormazabal. Rodrigo is a senior research scientist at LG AI Research, where he leads AI-driven initiatives in chemical science and molecular discovery. His work centers on building comprehensive tools and advanced reasoning agents that combine text, vision, and other chemical modalities to drive breakthroughs in molecular design and organic synthesis for scientific discovery. With an interdisciplinary background in chemical engineering, computer science, and artificial intelligence obtained at the Universidad de Concepción, Korea University, and KAIST, Dr. Hormazabal bridges domain expertise and machine learning research to accelerate scientific discovery and translate molecular insights from large-scale data into real-world applications. You have a really interesting topic. I can't wait to hear more about foundation models in chemistry, from structure-based pre-training to multimodality at billion parameter scale. Over to you.
Yeah, thank you for the warm introduction. I'll be sharing my screen. Yeah, so good evening, everybody. I am here, at least evening here in South Korea, where I'm based on. In other times, maybe good morning, good night. My name is Rodrigo Hormazabal. I work here at LGI Research as a research scientist. And today I'll be talking about foundation models for molecular discovery. I'll try to focus on what are they good at, what are they not really good at, how are they trained, and how can these models be leveraged today in order to try to accelerate the discovery pipeline. As a way of trying to sort of contextualize where my perspective on this topic come from, first of all, I will explain a bit about LGAI. Our company is part of the LG group. So in LG, LG has many different businesses and many different sort of downstream processes. So our company, one of the main goals is to try to help other LG affiliates in AI-driven initiatives in many different domains. Particularly the one I work on, which is the materials or molecular discovery domain. So we have many partnerships and working on different projects, so from batteries, displays, or bio applications. So I think this is the first point I want to sort of focus on, is the fact that I look at foundation models, or this idea that I will be explaining a bit more in detail, because they can be leveraged to sort of quickly iterate or repurpose sort of the knowledge we already have, or the hundreds of years of scientific knowledge, in order to sort of quick start new applications and hopefully accelerate them in some way. So that is the main sort of twist I will be giving to my presentation. This is sort of like a must slide. If you have seen presentations on this particular topic, most people talk about why is it hard to find candidates or characterize them. And the main problem, as most of you already probably have heard, is that by sheer sort of combinatorial explosion of the possible sort of structures, molecular structures, so we could make, we cannot just approach this problem by just searching or experimenting, because there's too many combinations. Maybe the synthesizable space is much smaller than the one I'm showing here on the left. But normally the bottleneck is that it's really costly to run experiments, to adapt to new pipelines, to start gathering data for new projects. So normally we are in a way constrained by the limited amount of experimental data we have. And here is where foundation models can actually help. These days, the word foundation model is a bit of a buzzword in a way, because of all the success these models that have had in the vision domain, or language, or chatbots. But I think the same ideas can, in a way, be transferred to the scientific domain. And I think there are many good initiatives these days, new companies working on this particular intersection. So the main idea is that if we combine some sort of all of the knowledge that we have accumulated as society in a way, and we have a system that can scale or understand all of the scientific knowledge from different modalities. Normally people refer to modalities as just ways of representing knowledge, normally, for example, audio or text or images. Scientific knowledge is also really complicated and intertwined between, when you read a scientific paper, you need to sort of understand graph, tables, how they combine, some information is in a diagram and some of the information is in the text form. So we need models that can leverage all of this information and find or create new knowledge, even though new knowledge might be a bit of a debatable term, in the sense that it's not necessary that we completely extrapolate to areas that we haven't explored before, even though that is something we should strive for. Maybe even just recombining what we already have through hundreds of years of knowledge can help us accelerate all of our discovery pipelines. Another point that I would like to touch on is many of the techniques I will be mentioning, or the approaches, are not new obviously for chemistry or for science, right? Maybe it's the combination of approaches and computing and scale and data, which has been accelerated by other applications. There's so much investment in AI these days, and many of the techniques or the technology that is being developed can be sort of transferred here. And then in the end, I will be talking about our models or our approaches to most of these topics, and how can this be leveraged, hopefully today, to work on new properties or characterization or projects, or discovering new leads. So this also is a bit of a mass sort of slide. Maybe you have done something really similar compared to this. But the main idea is that we normally have to rely on our intuition and knowledge and literature, obviously, to design experiments and to create new hypotheses and test them. And normally this takes a really long time. And the sort of the big promise, which is also maybe a debatable point, how much AI or these data-driven techniques can accelerate this. So that's why I add this question mark here. So it will take months, days. That depends on on your opinion, maybe, until now. But we have seen a lot of acceleration in many different parts of this pipeline, where we characterize compounds, we synthesize them, then we test them, and then we go back to the workbench and go through this loop. So I think one important point is to try to understand where can we use these foundation models. Normally, when we work on new projects, as I was saying, there are so many downstream applications within the LG group that we tend to always see new projects. So how do we quick start them? So a good sort of rule of thumb is that you should always start by checking what is out there, right? What exists in literature, which kind of approaches or experiments have been done before, right? And to do this, you need to understand scientific literature. And hopefully we can find ways to do this automatically, or at least, even if it's not 100% automatic, sort of speed up this process. So we have some models here on the what we call deep document understanding side, which some of this work has been done in partnership with Elsevier. Then we have maybe the main part of this talk, which is property prediction. How to do the inverse design. So if we have a set of properties that we are interested in, and then we want to find leads, how can we design these structures using these sort of big foundation models? And a bit of synthesis prediction. How can we find what can we actually manufacture, make, or synthesize in a cost-efficient way? So one sort of the starting point of most of our projects comes from here. How do we translate something that might be in natural language or just in plain English? We want to make this. How do we translate this or map it to the models we can actually use or leverage? So, for example, I just write here a few examples from some previous projects, for example. First of all, we would like to maybe extract information from literature, maybe structural rules or information people found in the past. We might want to predict certain properties, for example, if they exhibit flame retardancy or they enhance batteries, for example, batteries performance. Or we might want to do virtual screening, right? Search for what is commercially available and find if we can repurpose something to accomplish what we want. Or we might want to generate structures or predict synthesis routes. So, for example, if something will polymerize, or what we can do something like retrosynthesis, or see what we can find from some set of starting materials we already have access to. And I think one point that I want to keep emphasizing is the multimodality of scientific data. I think obviously this is a known fact, but I think it's become more and more important and where most people are putting their effort. I really like this example from Grossman, from the textbook, where you may have some problem about the reaction mechanism, and then all the mechanism is explained in text form, right? And within the text, you mentioned functional groups, you mentioned structures, you mentioned reagents. So it's really hard to sort of understand all of this information at the same time and together, put them together. So I think we need to, or one of the parts that we need to sort of keep focusing on is how do we extract insights from these documents. So this has a long story in the scientific domain too. There are many approaches and papers and ideas how to go about this. But I think the more this, for example, language models keep scaling, the more opportunities we have to do this maybe in a more automatic way. So this is where our company, as I was saying earlier, some of this part of this project has done in partnership with Elsevier about recognizing chemical structures in literature and reactions, and maybe extracting tables and graphs. I left some of the publications here. You can take a look if you want. But the main idea is that this is one of the main parts where we can leverage foundation models to try to understand in a more holistic way scientific literature. So now I'll go into the foundation models for molecular property prediction. So here I put just a slide to sort of show which kind of data exists in terms of molecular structures. For example, we might have databases like Reaxys, where you might have compounds that have been reported in literature before, synthesized, or are purchasable. So we can have this data that has been, in a way, unlabeled. So we don't have maybe information about properties for these structures. But anyway, we can extract knowledge from this sort of raw data. Then we might have maybe higher quality, but a smaller scale. For example, conformational data, DFT calculations, you might have 3D important information that maybe you can, in a way, use for these models to learn more complex interactions. And then at the last sort of downstream part is we have actual molecular properties, things properties of interest to applications. That is where normally we tend to transform our needs, right? So we need a certain compound that, for example, the example I will be giving today is about coolants. Which kind of properties do I need for this to be a good coolant, for example? And then here I also listed a few papers, and here is maybe where the word billion parameter part comes from. The title of the presentation is we try to leverage all of the information that is here to sort of train a model that can be a bit more robust to structures we haven't seen before. Even if we don't have experimental data about them and we only have the structures, anyway, we show, at least in this paper, that you can anyway extract useful information that can then help your models work when you have limited amount of experimental data. And then as you go, then we have models that use this 3D information, and then the last part of the normally the model that sort of predicts a particular set of properties is this multitask model. So we have many properties. For example, in Reaxys, you might have more than 20 million records reported the experimental properties for really various properties. For example, a melting point, boiling points. You might have many tasks. With task here, I refer to experimental data. And then the idea is to train one model that can predict all of these properties at once but by explicitly sort of encouraging the model to try to connect these properties. So maybe if you know something about melting point, you can infer something about boiling point, even if you don't have experimental data for a certain part of chemical space or type of structures. And this is where sort of we found a lot of value when we work on new applications. And also one part I would like to mention is, beside predicting properties, for example, we also, we here at LG, we are developing our own language models, and we try to find ways to align them with scientific knowledge. So hopefully language models can understand better chemical structures, so we can, as I was saying at the beginning, extract knowledge or use these insights that we get from the textual information to better predict certain properties of interest. And here's where but this is a branding name of our model. It's called EXA1 Discovery, and we have a full set of properties that we can characterize for molecular structures. So the main use case is we will have a company come and then explain what they want to design, and then we take whatever experimental data they have, which normally is a really small number of points. So normally they might have 12 points or maybe 100 points. And then they want to build a model that can estimate certain property so we can prioritize what to experiment on. And we have found that maybe just by sheer sort of expansion across looking at so many tasks or properties at the same time, we can find correlations that are not that easy to infer from just knowledge, right? From just reading papers, right? All of these properties also have their own bias. Maybe they are really constrained to the space you can experiment on, but maybe structures might decompose, or might be really hard to go to certain conditions to test some of these properties. But by looking at the other properties, you might be able to maybe find all of these interesting correlations. So I will go now into what does it mean after, let's say, you succeed at making this sort of big model that can do all of this stuff. How can you use it? The first, most logical or the primary use is you take a structure and then you modify it a bit, or maybe with the chemists normally want to sort of, or the way they probe or that they test this model is, okay, let's modify this. Does this sort of make sense based on the knowledge we have about the mechanism of certain property? So the good thing is we can do hundreds of or thousands of structures per second and predict all of this set of more than 30 properties that we can predict right now. For example, here we have melting point, density, dielectric constant. And we found that by training all of this together, we get really big improvements that are the most significant when we have really small data sets, which is normally where we are interested, the sort of task we are interested in. Then the other part will be to find sort of interesting insights from data. So maybe you might get something from literature. You might know that boiling point and flash point are correlated in some way for most structures, and some other properties might depend. Maybe liquids have certain correlations and maybe solids have different ones. But if you see this from the perspective of a foundation model that can predict all of these properties at once, we can find maybe other, not that like easy to catch correlations. So maybe we get new data and we realize, look, it correlates with all of these properties, so we can sort of quickly pivot. Okay, let's find maybe experimental data on all of these properties and then try to estimate better this maybe really expensive experiment, or so we can accelerate, as I was saying, the discovery pipeline. And then also we have models to do inverse design. So this is related to the example I'll be giving in the next, is if we have a set of already known sort of ranges where we want our molecule to have certain properties and certain ranges, we can give the model the property ranges and let the model sort of find and generate structures that hopefully match this set of specifications. Obviously, if this from the perspective of the model, then we need to do all the experimentation and and there's many steps on this process. Also see if the synthesizable compounds and a set of other sort of steps that you need. But I think this already helps you explore much faster. And in many of the applications or new applications, you normally want really restrictive, like really specific sort of areas of certain properties. So just doing search is not good enough. You need a model that tries to explore explicitly these sort of cases. And then I'll finish by talking about, as I was saying earlier, about this single-phase immersion fluid for data centers. So I just put an example here. The idea is that you submerge whatever you want to cool. In this case, data center equipment. And as you can see, with time, models are much more powerful, but they also generate much more heat. So we need new solutions to solve this. And this, I really like this example because there's this Open Compute Project initiative where there's a set of specifications for data center equipment, and they sort of go in detail about all of the properties and ranges that they should be fulfilled to create a material or a coolant that can be used in data centers. So you might have many different areas of things that have been explored until now, but they all have their drawbacks. So it's really, really hard to find structures that match all of the properties that we need, and they don't have all of these downsides. For example, natural oils might be good, but they have impurities. So all of them might have some trade-offs. So to finish, I would show sort of a video of how we'll go sort of our way of kind of interacting with the models. As I was saying here, you have this Open Compute Project, and they show a set in their white paper. They show a set of specifications. For example, here you have critical temperature, pour point, boiling point, and you have ranges. And in our platform, which is called Discovery Node, you have something similar to note-taking apps that are pretty popular. And the idea is here we equip these apps with the ability to use our models. So for example, here you can do molecular generation, and then you can choose properties and ranges. And then, for example, here we are choosing boiling point, melting point, the electric constant. And all of these ranges might be really hard to find all together at the same time. So that's why we need, in this case, a generative model, and the model generate candidates. It might take up to 30 minutes, but it tries to explore and try to find all of these compounds that fall within these ranges. So here you get the compounds, and then you get the predictions, and then you can keep interacting with the platform and maybe finding synthesis routes or finding similar compounds or predicting other properties. And this is kind of one of the ways we sort of try to kick off our new projects or initiatives. Yeah, I think that will conclude the presentation. Thank you.
Thank you very much, Rodrigo. This is really interesting. And to a point, I think it even opens up the possibilities of chemistry for non-chemists when you can ask your question in natural language. Is that something that you have on your radar as well?
Yeah, so there has been many iterations of sort of how we want to interact with these models. It's not something that easy. You need to actually put some solution in front of chemists and hear their actual feedback, how they want to interact with it. But I do see the ability to be able to interact in natural language, explain all your ideas, and then maybe iterate in this way. I think is a really important point, not only for chemists to explain their perspective, but also maybe easier to connect with existing knowledge, or maybe these models these days that can integrate databases of papers and stuff like that, and maybe it's much easier to brainstorm in this way.
Yeah, thank you. I see a question, and in my mind, I connect it to the last example that you gave about the coolant fluid, which I think was an example of then just bringing it to a lab and trying to synthesize it and then try it out in real world. But the question is there a way to quantify uncertainty in foundational models' outputs, maybe before you take the step of bringing it to the lab?
I think that is maybe one of the main areas to where people need to keep researching more. I think one thing that is maybe well known, on if you have interacted with platforms like chatbots and models, hallucinate or create knowledge that's fake, or is sort of plausible but it's not true. So there are many techniques that are being developed to actually evaluate the uncertainty by looking at other structures or looking at literature and connecting on sort of this multimodal way. But it's certainly, I think, a critical point that we need to keep researching on.
Yeah. And then a question that came through my mind is around making the step from, I guess, predictive models to more reasoning models. Is that something, or how do you and your group approach that?
Yeah, so there are many ways, I think, there are many areas on this pipeline sort of that are affected by the reasoning part. Normally people call it like level 2 thinking, like actually planning and scheduling and doing all of this. And I think the combination of this with maybe autonomous labs is something really interesting. How can models actually see the world and make inferences and interact with humans? I think having these models maybe explore using many tools, for example, that is something that maybe is in other presentations of today. I think this is super worth sort of pursuing endeavor. And I think it seems like the world is, or some part of the world, at least people working on this are going more in that direction.
Yes. And then there's a question around how can we evaluate the extrapolation ability of foundational models, especially for novel compounds? And maybe on top of that, do you also use then a feedback loop to reinforce the outcome when it's assessed by human chemists?
Yeah, so also today I only mostly talk about property prediction, but I think this is super interesting maybe for retrosynthesis, for example, like human in the loop retrosynthesis. There are so many things that are really hard to explain with numbers, right? They are not made for computers. So I think extrapolation in general is a really, really important topic. The main problem I see is, for example, in the language domain, and I think that is sort of good, right? We can take a lot of examples from what is happening in other areas. It happens that it's really hard to evaluate models because they consume so much data that they have seen most of the stuff you already have access to. So it's really hard to evaluate if they are they actually doing something new, or are they sort of just reprocessing what we already had before. So in this particular scenario of the properties, we have two ways. One is for a single property, can they really infer properties for new compounds, right? For compounds that haven't seen before. And the second one is, can they extrapolate to new properties, maybe for the same structure, but a new property. I think for new tasks, that is maybe a bit easier because we might have smaller data sets and we can test and leave one out and see how they work. But for structures, it's really hard to know if these foundation models already seen the structure, how much information they have about it. So I think this also is some really critical point where we need to keep researching on.
Thank you very much. I think it's hugely powerful that your group sits in this large conglomerate where you also have access to all of these groups that take your chemistry or the models that can help their chemistry in real business application. You do a lot of wonderful things. Thank you for showing some of that to us today. Thank you also for our audience for asking the questions. Again, there's a short 5-question survey available in the chat. It's the red box. Just click on it and help us by giving us your feedback. We bring this session to a close and the platform will automatically move you to the next session. So just sit tight, hang on for a couple of seconds, and then the platform will move you over. Thanks again, Rodrigo. It was a pleasure having you, and have a wonderful day.
You too.